Okay, first thing I'm going to say is if all 20 of you watch this on your Chromebooks at the same time, it's going to be really annoying because everyone's off by like 1 second. So please put headphones in. I know y'all got headphones. Maybe share an earbud with a partner if you don't. Pause the video to take notes as you need to. Thank you. What's up everyone? I am gone in Grand Junction today with the marching band, so I'm making this video. I don't necessarily like the AP video that they have about chromatography and distillation, so I'm going to explain it to you myself. These two things are about liquid separation. If I have a mixture of 2 or 3 or 4 liquids, how do I separate them chemically? And there's 2 ways to do that. It's either distillation or chromatography. We're going to start with distillation. It's super easy. Pretty much everyone knows what it is. It separates things on their boiling points. Based on their boiling points, you just put a fire under your flask and the lower boiling point thing boils off first. You collect it, and then whatever has the next highest boiling point, you crank the heat up to that. Then that will boil off. You can separate liquids that way. It is very cheap, creates no waste, which is a really big deal in chemistry. And can be done with really large batches. I mean, you can distill a whole barrel of something. The cons are it's not a perfect separation method. So the example that I like to use, and it's a good example, is moonshining. So I'm not going to go into the details about exactly how they make moonshine, but when they're done making moonshine, these moonshiners get a big jug, and it has all these chemicals in it. It's got methanol, fructose, and glycerol, and propane. These are all byproducts of the fermentation. The yeast that they put in there has lots of protein, so they have proteins which are really big and have lots of ionic bonds. And it also has ethanol, which is the drinking alcohol molecule. So the moonshiners, they take this big mixture of everything, they put it into their distilling apparatus, and I want you to pause the video and rank all 6 of these molecules from the what's going to distill off first and what will distill off last. And so talk about this with your partner. Pause the video. I'm going to unpause now. Going through some of these, the protein won't distill at all. It's ionic, it's a solid. You're going to burn this well before it'll ever even turn to a liquid. So this is just going to stay at the bottom. On the other end of the spectrum, I see propane, all hydrocarbons, very, very nonpolar molecule. And what happens is after you're done fermenting, you kind of take the top off the barrel and it goes psss, and all these gases escape. And that technically is some sort of distillation. That is propane gas. We don't even need to heat it up. Room temperature is hot enough for it to be a gas because it's so nonpolar that it just leaves. Looking at these 2 molecules, fructose and glycerol, I see lots of carbon-oxygen bonds. Those are polar, so there's going to be lots of dipole-dipole forces. They also have lots of OH groups, so there's going to be a lot of hydrogen bonding. These things are going to distill off near the end. It's going to take a lot of energy to distill these, so they'll kind of stay in the barrel for a while. The last 2 molecules I want to talk about are ethanol, which is the actual drinking alcohol molecule, and methanol. What you see if you go on to Netflix and watch one of these shows about the moonshiners is when they're distilling, they get the first cup and they hold the cup up to the distiller, and they fill the first cup up, and they just throw it into the woods. They throw it out. And you're wondering, well, why is that? And that's because methanol is the molecule in moonshine that makes you blind. And if we look at the forces of these, ethanol has an extra carbon on it. It has a longer carbon chain. There's going to be stronger London dispersion forces. So you were correct if you said methanol is going to distill off first and ethanol will distill after that. And so what those moonshiners are doing is the first thing that's going to come out of here is the methanol, and they're collecting that in the first cup, and that's the bad molecule, makes you blind. They throw that out, and then they start collecting the ethanol, which I think is pretty funny. Like you're watching that show with your friends, and they go, why are they throwing that cup out? fundamentally, you can say, well, actually, it's because ethanol has one longer of a carbon chain, so its London dispersion forces are greater, so it's going to stay. It's not going to. It's going to stay in the distilling barrel longer, and they're going to look at you like you're crazy. But I think it's cool. The second reason I really like this example is it reminds us that distillation is not a perfect separation method. So they distill their first batch, and it's actually only going to be about 60% ethanol. A lot of it is water. You're going to have some of these other molecules in there as well that distilled over early, and it's only about 60% ethanol. So they put 1x on the jug to say it's only been distilled once. Then they have to distill it again, and they can get it up to about 90% ethanol, and then they distill it a third time, and that gets us this cartoon moonshine jug that we all know and love. It's got 3 X's. Those actually mean something. That means it's been distilled 3 times, so it's really high strength, and they have to distill it 3 times because it's not a perfect separation method, which is why I like this example. That's a good way to memorize pros and cons of this. Okay, the next kind of liquid separation technique that we're going to talk about is something called chromatography. You're going to do this all the time in chemistry. We're going to do this tomorrow. We're going to do this a couple times next week. And you take your liquid sample here, these dab in this brown liquid, you put it on this thin chromatography sheet, and this chromatography sheet is just a thin white rectangle of extremely polar silica. You dot your sample on like they're doing in this GIF, and then you put your entire sample in a beaker or a vial with a solvent in it, and the solvent starts traveling up the sample, and you can see it traveling up by capillary action right here. And what happens is a time-lapse GIF is the sample will travel and be carried along as the solvent travels upwards. And we can see, like, if this is a mixture of 2 liquids, these 2 liquids are being separated out. So it's a liquid separation technique. Here is some vocab you're going to need. The solvent is called the mobile phase. That's because it's moving up this chromatography sheet. That's easy to remember. So the solvent, or the mobile phase, carries the sample up this very polar plate of silica. So this white sheet that is polar silica, that's the stationary phase. That's because it doesn't move. It just stays there in the beaker. That's easy to remember. So here's an experiment we did. I took a sample. There was a mixture of a couple different liquids. I didn't know how many. I didn't know which they were. I dotted it. I put it in some solvent. The solvent carried this sample up and separated it out, just like we can see in this GIF here. So the question, I want you to pause this video and talk about it. First off, how many molecules are in this original sample? This is the before and the after. And then, this is the more difficult question, what molecule out of these 4 was the most polar? And how do you know? So pause the video, talk about it, take your guesses, and then we'll talk about it. Okay. Going back here. Answering these, first question is pretty simple. There are 4 different molecules. I can just see, and that's what's so powerful about this chromatography. I can just look at it. There's 4 molecules. The second question is more difficult. Which molecule was the most polar? So when we think about this, we have to remember that this sheet that they're sticking onto is also very polar. This silica is very polar. So the question that we're going to say is, well, which of these molecules, 1, 2, 3, 4, is going to hold on and cling to that sheet the tightest? Because we have this liquid washing over it, trying to carry it upwards. And so if you said this like light brown was the most polar, you would be correct, because what's happening is this solvent is trying to push everything upwards as it travels upwards, and this little brown dot says, no, I'm sticking onto this sheet. It is so polar, it has lots of polar-polar, dipole-dipole interactions with the polar plate of silica, that it's just staying where it is. It is sticking on that sheet. Whereas if we look at this dark green dot, when the solvent hits it, the dark green dot says, I don't care about sticking onto this sheet. I have really no interactions with this sheet. I'm just going to ride the wave and just get pushed up willy-nilly by the solvent. So I know it doesn't really interact with the polar silica. Therefore, it must not be very polar itself. There are many solvents that you're going to use. I mean, there's like 60 different solvents that you could use for the mobile phase, and that's what tomorrow is going to be about, is using different solvents. And they can range from non-polar, so you can use just straight hexane for your solvent, to very polar. We use a very polar molecule called ethyl acetate. Sometimes you'll use acetone as a very polar molecule. We're going to look at this more tomorrow, but just to get a better feel for thin layer chromatography, we got an experiment here. I got a brown liquid. It's before and after. We can see the solvent has traveled upwards, and it's separated it into its two liquids. So in this experiment, the mobile phase is a mixture of 90% hexane, which is nonpolar, and 10% ethyl acetate, which is polar. And what's happened is it seems like both these liquids are superpolar because they're sticking onto the plate. They're not really moving that much, even though the solvent moved all the way up here. So the question I want you to pause and ponder with your table group: how can we adjust our solvent to fix this problem? And if you remember, it's about 90% nonpolar, 10% polar mix. So pause and try to answer that question. Okay, the answer is we need to make the solvent more polar. So in this example, this solvent is not interacting with our sample enough. It's just washing over because it's 90% hexane. It cannot have strong intermolecular forces with our very polar sample. So we need to make the solvent more polar. So we could go to something like maybe a 50-50 mixture. If we changed it to only 50% hexane nonpolar and bumped ethyl acetate to 50% polar, what happens now is when the solvent is traveling upwards, you get a lot more dipole-dipole forces between our sample and the solvent that's washing over it. That's going to cause these to be pulled up more, and we get good separation. Now we get good, clean, 100% separation. Another vocab term that you're going to have to do, it's going to be an MCQ question or an FRQ question, it always is every year, is we call it the retention factor, or RF, R little subscript f. It is extremely simple. It is the percent of the thin layer plate that the compound crawled up. You compare it to how far the solvent went, and it's in decimal form. It's extremely simple. So if I look at, I got my sample and it's separated into compound A and compound B. And again, you pretty much just eyeball this. I don't even care about a good measurement. The solvent went here, but A only went about 40% of that way. So the retention factor of A is 0.4, 40%. It's in decimal form. Again, it's super easy. You can just eyeball these. It's nothing serious. Same thing, B has moved about 80% of the way that the solvent went. So it's the retention factor, the RF of B, is 0.8. We use these in literature, so when you're writing a paper and you're making a new compound, you can characterize it and say, oh, the retention factor of this compound is 0.7. So the pros of thin layer chromatography: there's perfect separation. If I look at this, that is the orange molecule, that is the red molecule, there's no mixture. And it also allows us to see the relative polarity of molecules, which is super, super, super powerful. I can see that this red dot, this red compound, is just more polar because it's sticking onto that sticky polar silica gel. The cons is it uses a ton of materials. It uses a ton of solvent, it uses a ton of silica plates, and we just throw the silica plates out, we get rid of the solvent, and it can also only be used for really small amounts of liquids, like 5 milliliters, which is barely anything. If you're working in a small synthesis lab, that's enough, but otherwise, it's not great if you're trying to do this on an industrial scale. So the next kind of chromatography I'm going to talk about, it's called column chromatography. It is very, 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 very similar to this thin layer chromatography. It uses all the same exact logic, except now this is showing over time. So this is 1, 2, 3, 4, 5 over time. So we start with a column, a glass column. We load it with polar silica gel, and then we put our sample on top. Then what we do, I'm going to pour in my mobile phase. I'm going to pour in my solvent, and that solvent is going to start to push my sample downwards, and it's all going to start to come through the bottom, and we're going to collect it at the bottom. And we're just going to keep adding more and more of our solvent on top, and it's going to keep flowing through, and it's going to push our sample closer and closer to the bottom. And what I see by the time we've hit, frame 3 or time 3 in this is that what started as a mixed sample, they have now separated out. And as we can see, it's labeled in this diagram. The orange compound has stronger dipole interactions. It is sticking in this blue polar silica gel, and so it's a lot harder to push down this blue polar silica gel, whereas this green compound is probably more nonpolar because it's going to come out of the tube quicker. It's not sticking in the polar silica gel very strongly. So then eventually the green compound will come out first because it's not as polar, it's not sticking in that silica gel. We wait a little bit, we go to the next frame, and then we can collect the orange compound. It's very similar. It's pretty much just thin layer chromatography upside down. So I took that GIF from earlier, I flipped it upside down. We take our solvent. The solvent is now moving downwards due to gravity, and it's just separating those molecules out. The most non-polar molecules are going to come out first because they're not sticking to that silica gel. So we go back to the original example. I have my sample. This is the before and then after. I do a thin layer chromatography sheet. I see that it comes out in 4 different molecules. This is the new question. I take my purple sample that's the mixture of everything. I put about 5 milliliters of it in this column, just like frame 1 here. And my question is, which molecule is going to elute first from a column? Elute's another vocab word. It's just chemistry for come out. So what molecule is going to come out first from a column? So pause, try to answer that. If you said the dark green molecule is going to come out first, you are correct. That is because in this thin layer chromatography experiment, I can see that the dark green molecule is sticking to the silica gel the least. It has the least amount of intermolecular forces. So you can think of that thin layer chromatography plate, flipping it upside down. That means when we do this column chromatography, it's going to shoot right through that polar silica gel. It's not going to interact with it barely at all, and that's what's going to come out first, which is pretty cool. The last thing that we're going to talk about, and if you go into chemistry, you're going to use this. You're going to use this all the time. It's ubiquitous in chemistry. It is a chromatography mass spectroscopy setup. So you get a solvent, and you get a computer to regulate how much solvent is coming in. You put your sample in. This is column chromatography, or this is tube chromatography, I'm sorry. It's exactly the same. It's just another kind of chromatography. The logic is exactly the same. So I have this windy column here. It's packed with polar silica. So I put my sample in, I put solvent through. The most nonpolar things are going to shoot out of this column first because they're not going to stick in this column or this tube. The more polar things are going to take their time because they're going to be sticking and having dipole-dipole interactions, maybe hydrogen bond interactions with the silica gel. They're going to stick in there. They're going to take a lot longer to come out. So we take this big tube chromatography apparatus, we hook it up to a mass spectrometer, and this is a $3 million machine you can buy. Every lab has one. Is a chromatography mass spec because it's super powerful, and we're going to investigate that today. The column, the chromatography can help us tell how polar the molecule is, and the mass spec just tells us the molar mass of that molecule. And those two things combined are extremely, extremely powerful. So your task for today is you're going to be looking at some data from this experiment. This is some Norwegian scientists. They were doing environmental studies. I don't even remember what it was, but the winter came and they had 4 months of downtime and they had all this crazy expensive experiment or equipment. So that they couldn't use for 4 months in this environmental study because it was winter. So they took all their expensive equipment and they brought it to a movie theater. And here, I love this guy. He's so happy. They hooked it up to an air duct of a movie theater to see if humans breathed out different molecules when they were watching scary movies. Because we breathe out thousands of different, really, really low concentrations, but different volatile organic compounds. And they were saying, or they were seeing, if there were spikes in different molecules, if we breathed out more of different molecules when we're scared. So this is the paper right here. You can read it if you want. Cinema audiences reproducibly vary the chemical composition of air during films. So this is the worksheet that you're going to look at. Maybe they were Austrian chemists. It's all the same. So they found 5 different compounds in the air that were released from human breath when we're watching a scary movie. And the data that they got is from this chromatography mass spectroscopy experiment. So compound 1 took 40 seconds to elute. It's shot through that chromatography tube. And I can see it has an atomic mass of 44, molar mass of 44. Compound 5 took a lot longer. It took 16 whole minutes to get through that tube. This is where we're wasting a lot of solvent at this point. We're using a lot of resources. That's a con of this. Maybe you have to run solvents for 16 minutes. But compound 5 has a molar mass of 74. We get that from the mass spec, and it took a long time to come out of that column. So your job today, and please do this with your partner. This is a lot of data to look at yourself. You do not want to look at this and try to find all these molecules yourself. But we have 20 possible suspects for all these molecules. And you have to say, oh, compound 1 is this thing, and compound 2 is this thing. Use your knowledge of chromatography, use your knowledge of mass spec, and solve it. There's not a place for your name. Write your name, turn this into the basket, and I'll see everybody on Friday.